Okay, are you ready, Robert? Can you hear me? Yeah. Okay, so it's 2 o'clock. So it's my pleasure to welcome you all to this first Nora Friday afternoon webinar. So Nora had actually planned a yearly conference in April. We had to cancel that conference, unfortunately, due to the corona situation. And now we have invited several of the speakers to have weekly talks that they were supposed to have at the yearly conference. So first out is Robert Jenssen today. And this is hosted then by Nora. Nora is the Norwegian Artificial Intelligence Research Consortium. So we have 9 partners, 7 universities, and Simula and Norse. And University of Tromsø is one of them. Robert Jenssen is a professor at the University of Tromsø. He is a leader and the head of the Machine Learning Group in Tromsø. And today his talk have the title New Advances in Deep Learning with Applications in the Monitoring of Power Lines. So I think we should just, before we start, give some general rules. By the way, my name is Klaus Pettersen, and I'm the CEO of Nora. We will continue. The talk will last for about half an hour. Then we have a questions and answer buttons below the screen. So please write your questions in the questions and answer panel. It will also be possible to open up for oral questions. So you could also raise your hands in this system, and I can open up for oral questions. So with that introduction, it's a pleasure, Robert, to give the screen to you. Thank you.
All right. Thank you so much. So first of all, let me just thank Nora and Klaus for this opportunity to give this talk. Very, very happy about that. Also happy to have close contact and I think a very good collaboration with Nora, so very happy about that. As Klaus said, my name is Robert from the Machine Learning Group at UiT in Tromsø. So before I go into the details of this talk, and before I forget, just want to mention some of my collaborators and thank them in advance for being part of this work and being part of our group. And especially, as you can see on the right, Nan. He was an industrial PhD student in our group together with the company eSmart Systems in Halden. And he is basically the main man behind much of what I'm going to tell you about today. And also David, as you can see in the middle of the screen, bottom part, also his supervisor together with me on his industrial PhD project. So before I go into the contents, which is about advances in deep learning made in our group and especially together with eSmart Systems, let me just tell you a couple of things about our machine learning group. So we've had machine learning activity since 2005 at an international level, and we've been growing steadily as a group. So now we're counting about 25 members, faculty members, researchers, postdocs, and so on. So if you're ever interested in coming to Tromsø, please come visit us. And you can also see the website address at the bottom of the slide. What we do in this group is several things. The common theme of the group members is basic machine learning and AI research. So that means going to the math, develop new methods for new problems to analyze different kinds of data. So the kind of foundational machine learning research, and there we publish in machine learning, neural networks type of conferences and journals. At the same time, lots of activity towards computer vision and analysis published in computer vision conferences and journals, and also a very, very big activity on machine learning for data-driven health. And also recently, activity towards energy, renewable energy. And also, as Klaus, for instance, very well knows, we organize a workshop in January each year called the Northern Lights Deep Learning Workshop. I would be very happy to see many of you listening to this talk right now in January 2021, either physically or online, depending on the conditions. And in 2020, we also had a Nora panel debate at this workshop that went very well, that Klaus headed. And we had session chairs at this workshop from basically all the universities in Norway. So kind of gathering the community in Tromsø in January for this, this workshop with around 150 participants in 2020. All right, so let's get to the specifics of this presentation. So the presentation is, on the one hand, very, very applied. So basically, we can trace the activity to this industrial PhD project I talked about. And it's basically within the context of monitoring the power lines in Norway from drones using computer vision based on deep learning. But at the same time, as we have been working on this very applied project, several sort of basic research challenges has arisen. And I will try to tell you a little bit about these more basic research challenges that we have been trying to solve. So together with eSmart systems, we are researching new ways to try to monitor the power lines in Norway from images taken by drones and helicopters, and basically using deep neural networks as the backbone for the image analysis. The task is to try to figure out whether everything is okay with the power lines, if there's some problem, if there's some components missing, without having to send people manually out in the field to inspect these power lines. So it's a sort of automation process that we're trying to achieve. And this project and this work has been a big, big task. I'm not going to spend too much time on this first part of the talk. I'm just going to try to convey that the main purpose of the talk was to basically engineer deep learning solution to do this monitoring of the power lines as good as possible. And several challenges from this very applied project then comes in our way. For instance, to have the training data needed in order to detect objects, localize them, and figure out what kind of objects that we have in the images. So that's been quite a big part of the work, just to gather training data and to annotate training data, because as you probably know, in these kind of machine learning systems, we most often need annotations. So we need labels of what kind of objects are in images and where in the images they are. And this most often will require manual annotation or labeling. So a lot of work has gone into that part of this project. We've reviewed the current state of the art and proposed a solution. And in this solution, basically it's not just one kind of network that analyzes these drone images of the power lines and try to localize objects and then recognize objects within certain locations in the image, but several networks together. So what we basically, after a long time of working with this, discovered was that we needed networks that had several different purposes. For instance, one network just to detect and analyze the mast of the power line. And then several other networks to go into more detail on different parts of this mast. So that's what you can see in this slide. For instance, top cap classifier, pole classifier, cross arm classifier, in addition to kind of the first network, which is the mast detector itself. So what I'm trying to say is a lot of work, engineering type of work, not really much new solutions on the mathematical model of the neural network, on how to optimize the system, this kind of engineering work, very applied project. And what came out of this project was a running system that you can see on the left, where it says multi-stage model pipeline. So this is our system now in real time running, as opposed to the system on the right where it says single model, which is just one big network to try to do this task. As you can see, we really need the multi-stage approach that we have developed, where you can see that first the big object is detected, which is the mast itself, and then the smaller objects are detected and localized and recognized by other networks. And all of this is trained end-to-end in one big operation. So what you see, the rectangles, there we localize, okay, there is some object here. And then within the rectangle, we need to figure out what kind of objects do we have. All right, so this has now led to basically an operational solution in this kind of collaboration between academia and a company. So it's been a very, very rewarding journey to be part of, and basically due in large parts to Nan, this industrial PhD student, which has done a brilliant job. However, what I'm going to spend more time on now in this presentation is some more challenges that has come up during this work, where there are no solutions today to engineer and to sort of just to pick some tools out of the shelf, where we had to go to scratch and basically develop the new systems ourselves. Two things. One is how to detect the power lines themselves, because now we're basically talking about manually steering drones over the power lines. But what if we could detect the power lines automatically and then maybe have autonomous drones fly over the power lines by a detection system? Another thing is that in this previous system I talked about, where we have the multi-stage approach, there we had training data. It's been a big effort. But what we've seen is also that new types of objects, new classes, for instance, certain faults on the power lines could arise over time. So basically we didn't have these faults or these categories when we trained. But as time progresses, new classes of objects arise, and then the systems cannot cope with them. So how to deal with previously unseen components and faults, that's the second basic research challenge we've been trying to tackle. And this has led us into something called few-shot learning. So I'll come back to both of these things in due time. Let's start with the first challenge, detecting the power lines. So this will lead to a system called LSNet, Line Segment Net. So this is a new network and a new approach proposed by us. And we have submitted a paper where we describe this new system. All right, so the idea is to detect the power lines and to have the drone potentially navigate based on the detected lines. So self-driving UAVs. So there are no really good systems for this as of today. If such a system will work, it has to be very fast, because the drone flies there online, It can't wait for some big processing step. Has to be fast, and this is what we have tried to achieve. All right, so this is deep learning. However, this challenge with training data that I mentioned previously, when we made the system to localize masts, cross arms, insulators, and so on, and then to categorize them into kind of good or faulty condition. How to do that now with the power lines? So in order to avoid having people, manually labeling pixels in thousands of images, here we have a power line, here we do not have a power line, and then to try to train some system based on that, we've done something radically different in this project. And this is key. We've had a very good collaboration with a company that synthesizes this kind of data. So basically make images which are not real, but which are realistic, of power lines with mast, crossbar, and everything. And the good thing is that, of course, now, since we made the data ourselves, we have complete control over it. So we know which category every pixel belongs to. So for instance, we know where we have all the power lines in these images. And the system we're going to talk about now is trained fully on synthetic images. No real images, only synthetic images. But then, of course, in the test phase, in the operational phase, then it works on real images. So here you can see synthetic images. This is not real. It's made by this company, Nordic Media Lab, in collaboration with eSmart Systems and also us. And this is what we will use to train our new LSNet. But what is the LSNet? So this is a new thing. So the line segment net is based on a deep neural network, deep convolutional neural network. We have chosen to be inspired by the so-called VGG16 network. The important thing is that the VGG16 in this case acts as a feature extractor. So it takes training input images, feeds them into a certain convolutional neural network, which is the VGG16, and it gives out features to represent these images. What we then do, which is the core idea of this new method, is to divide images into grids, so basically smaller patches. Then in each patch, we do two things. We make a classification. Do we have a line in this patch or not? And if we have a line there, then we try to predict the two endpoints of the longest line segment in the cell. And we have many cells. And the way we create many cells is a special way that we will now have a look at. So as you can see, we have one big feature extraction network, and then we have several other networks for the classifier part, for the regression part, and they are all trained in one big end-to-end operation based on synthetic data. So this is the core idea, and this is a new idea. So let me now try to explain how this works. Again, synthetic data. Once we have the synthetic data, we can of course do all these kind of data augmentation tricks that we very often used in deep learning. Rotations, add some noise, change the background and all that stuff to create a bigger training data set. And we do all those things also in this case. Now I mentioned these grids, that within each grid in the training part, what we do is we try to classify, is there a line here or not? And then to try to figure out basically the end point and the start point of the longest line. To have a grid-based approach to deep learning is not new. Maybe you heard about something called YOLO, you only look once, which is maybe one of the most famous object localization and object detection networks that are out there. They implement one type of grid approach where you basically divide your image into a certain number of non-overlapping grids. we do something else because we can actually divide our image into overlapping grids. And this is important because, as I said, we want to classify whether we have lines or not in a grid, but we have some border issues between the grids. And we want to take care of that by having overlapping patches or grids. And we can do that by paying close attention to the properties of convolution. So I said convolutional neural networks, and it means that everything is based on properties of convolution. So let's have a look at how we do this basically. All right, so these non-overlapping grids, we have our classification, our regression task within each grid, but how to basically implement non-overlapping grids and to do the training in what's called one shot. It means that everything is trained together, even the grids. All right, so let's have a look at this. So what we have chosen to do is to work with 512 by 512 input images. This is pretty standard when it comes to the VGG16. Color images, so we have 3 channels, RGB. Now in this VGG-inspired network we have for the feature extraction, we have 4 blocks of convolution. So we have block 1, block 2, block 3, and block 4. And then at the output of block 4, we have what we call 2 transformer networks to implement these grids, and then classifier network and regression network to do the job within each of these overlapping grids. So let's first have a look at block 1, block 2, block 3, and block 4 when it comes to the feature extraction. Just to sort of repeat a little bit for those that are not familiar with VGG16 kind of networks. What's going on? All right, so have a look at this. So we have a 512 by 512 input image. What we do now, since we have convolutional neural networks, is that we perform 3 by 3 convolutions. We use stride of 1. That means that the convolution mask, which is this guy, it jumps 1 pixel at a time. Not 2 pixels or 3 pixels, it jumps 1 pixel at a time. Then, in the first block, we have 64 different filters that we want to learn. That means that at the output of the first convolution, we get 64 feature maps, as you can see here. And then we repeat this process several times, but as you can see here, we have a stride 2 convolution. That means that the convolution mask jumps 2 steps, 2 pixels, before the new convolution is made. And the effect of doing this is to reduce the size, the resolution of our input image by 2. So we started out with 512 by 512, and now we are at 256 by 256. And we have this kind of cube over all the 64 feature maps. So this is convolutional neural network and the way it works and the way that we reduce the dimension, the resolution by the stride. This was block 1. Block 2 now takes the 256 by 256 as input. We now choose to have 128 filters. After a couple of convolutions, we come to a stride 2 convolution here, which means that the resolution is once more reduced by half. So we have 128 by 128 at the output of block 2. And then we have a third block like this. We go to 64 by 64 resolution. And then block 4, we end up with 32 by 32 resolution. So this is not something I now made up. This is the VGG16 network. The important thing is that the output now of the VGG16 network at block 4 has a 32 by 32 resolution. Now let's look a little bit more at what's going on. This is before we go into the classifier and the regressor network to actually detect lines and then figure out, the orientation and the length of the line. So have a look at this. So now we are at the 32 by 32 output of block 4. It's important to realize that each element, each pixel of this 32 by 32 grid corresponds to, by the properties of convolution, to a 16 by 16 area in the input image. So each element in the 32 by 32 corresponds to a 16 by 16 pixel area in the input image. And this we will now utilize in the next step. So in the next step, we implement these overlapping filters I talked about. And after we do that, we have two networks, classifier and regression. So to implement the overlapping grids, we now use a 2 by 2 convolution on this 32 by 32 output of block 4 in the VGG16. So let's analyze a little bit what's going on now. We will also use 512 filters when we do this 2 by 2 convolution, and we use stride 1, which means that we will end up with a 31 by 31 area resolution after this 2 by 2 convolution. But let's now have a look at what's going on here in more detail. This is a toy example. So now you can think of this upper part as the 32 by 32 output of the block 4 of the VGG16. So then we do a 2 by 2 convolution, as I talked about, in the transformer network. So you have these 4 pixels, and they go together into the convolution, and they produce one number, right? Then we have a stride 1, so it means that we just jump one step to the right, and we perform a new 2 by 2 convolution. That produces this number. One important thing to note now is that this number is related to this first number, because 50% of the first 2 by 2 convolution corresponds to 50% of the second 2 by 2 convolution. However, when we jump one more step and perform our 2 by 2 convolution here, this number, which is the output of that operation, no longer depends in a direct way on this first number, because now the 2 by 2 grid has moved such that there's no overlap from the first grid to the second one. And this is actually key, because if we now go to this slide, you see that these red numbers, they do not overlap in the 32 by 32 output of block 4 in the VGG16. And these magenta ones, they do not correspond to overlapping areas in the 32 by 32. So actually the red ones and the magenta ones, they implement different grids that are not overlapping. However, there is an overlap between the red and the magenta ones. So actually you can see here that by being a little bit thoughtful with what convolution does, we can implement overlapping and non-overlapping grids that corresponds to areas in our input image, the 512 by 512. So this is key here actually. So this is the transformer part. So now we're done with the transformer part, and we go into the classifier subnet and the regression subnet. Let's do the classifier subnet first. So what happens now is that we want to predict basically, and we have two outputs, line segment or not a line segment in this particular patch we're now looking at. So what we do now is so-called one-by-one convolution. So this is still within the neural network way of thinking. It's just that it's one by one. So it means that every element here, which is in this 31 by 31 output of the transformer network, basically corresponds to a vector of 512 elements for each such. And then we can basically have two filters, one for each class, line segment or non-line segment. And this is what you see here. Two feature maps out, and basically this gives us class, line segment or no line segment in that 32 by 32 input image patch. Regression subnetwork, and now it's about trying to estimate or predict the two endpoints of the longest line segment within this image patch. Again, one by one convolution. Again, we choose 512 filters. This is a little bit arbitrary choice. And now we have four filters. Four because we have four coordinates, right? We have the sort of x coordinates and the y coordinates in this space of endpoints of the line. All right, so now we have a bunch of neural networks, feature extraction, transformer networks, classifier network, and regression subnet. And we train this based on our synthetic images. A couple of things to think about. We have a very imbalanced problem. Most of our patches do not have a line segment. So we have to be a little bit conscious about this and to choose a good cost function, basically. So we do that basically by going to something called a focal loss. Not so important, this part, just be aware that, you know, there are some challenges when you do new work like this. You have to be aware of the literature, and there's been some new developments when it comes to cost functions to counter class imbalance, for instance, focal loss, to use that. And also for the regression part, there has been new developments, new type of cost functions to basically have a good cost function to do the regression. And there's something called wing loss published recently that we also incorporate in our LSNet. And it turned out to be important. Now we train the system. It's end-to-end. All of these grids are implemented within the same training session. And this is the result on real images. So as you can see here, we trained on synthetic images, and now we test on real images from Norway, and we do a pretty good job on finding basically the power lines. I could show you more results, but I think I will stop with this. I'm just trying to say, basic challenge that came up during this work, and we had to solve it, and we did it with the LSNet. It's very fast in the operational phase. Right now, about 20 frames per second. So it's very close to being kind of online system. All right. For a few more minutes, let me talk a little bit about another basic research challenge that came up during this very, very applied industrial project. So I talked about this thing of having to handle the fact that, you know, the world changes. We train on some data, but then the world changes. And in the operational phase, when we, you know, we do our stuff, we test, we classify, new classes may arise. The network may never have seen these classes. So how to deal with that? There's no really good solution to this problem yet, but there's a very encouraging and cool sort of sub area within machine learning, deep learning, which is called few-shot learning. And here the aim is exactly to try to produce deep neural networks, convolutional neural networks, for instance, that do not commit too much to the training data you have, such that if you get even just a tiny bit of data, maybe even just one example of a new type of category or class that the network had never seen before, it's supposed to be able to adapt very quickly to this new type of category or class within your images, for instance. So this work that we did is more on the basic research side. It's not implemented with the drones and the power line system, but it could be, the plan is to do it in the future. So here is the setup. So what you have during training here in so-called few-shot learning is you have a few classes, let's say 5. You have a few examples from each class, maybe even just one. This would be called one-shot 5-way learning. And then you have to basically train or develop a deep neural network based on just a few classes, a few examples from each class, to work properly on a few test examples from these classes. And we do this in something called an episodal fashion of training. So where basically the network is exposed to a few samples from a few classes. It does some adjustments based on a few test examples. And then the idea is that even if you in the test time meet images that the network has never seen before, it has never seen the category. For instance, some kind of mushroom. You have not had this kind of mushroom in your training set, but now it's suddenly there in the test set. Then even if you just have a few, let's say 1 example or 2 examples of this mushroom and some other classes that are new to this network, very quickly you're supposed to be able to adapt to these new classes and then test with a good accuracy. So this is called few-shot learning. The most promising few-shot learning method is called prototypical networks, and this is the one we have improved upon with basic research in deep learning. So in prototypical networks, what you do is, in your meta training stage, when you have a few samples from a few classes, basically you compute an embedding. This is what all deep networks do. You basically embed or compute a representation for your data in your code space or in your representation. You compute centroids, means over the classes. And the idea is to adapt the system such that test points come close to the optimal class in terms of the mean or the centroid for that class. So a very simple idea, actually. And there's a cost function to do this. And what this slide says is that basically, as you train your network with backpropagation, you try to embed point Z close to the best prototype, basically the prototype that corresponds to the class that you know Z has, and as far away from the other prototypes, from the classes that are not the same class as Z, as possible. Now, why am I mentioning this? The thing is that a very active topic within deep learning these days is feature normalization, to try to make networks more robust, regularize them more. And one particular promising approach is to basically normalize somehow feature vectors. For instance, this Z embedding that I talk about now in the prototypical networks. And some very, very recent papers have tried to do this also by kind of forcing the length of the embedding points to be 1. So that means to basically embed all your points onto a sphere and then compute distances to centroids and do your optimization on the sphere. However, when you force the length of vectors to be 1 by just dividing by the norm of the vectors, you're not really doing scaling by the network. The network is embedding, but then you are forcing the scaling, and this is not optimal at all. It also causes optimization issues. So what we did as a basic research effort was to try to create a new type of network that would embed these points Z, which is the output of the deep neural network, onto a sphere, but at the same time close to the best prototype such that we can do few-shot learning in as good as possible a way. So we introduced a thing which is called a class conditional dissimilarity measure. And this is what I'm now going to just spend a couple of minutes at the very end of this talk to describe. So the concept is, and we call it SEN, so squared, Euclidean, and normalized dissimilarity measure. So what we do now is, if this embedding point Z belongs to class K, and we have the centroid for that class, which is CK, then we say that the dissimilarity between the point and that centroid is a combination of the Euclidean distance between the point and the centroid and the norm distance, as you can see here on this slide, with a plus epsilon in between. However, if Z do not belong to class K prime, so that means one of the other prototypes, then the dissimilarity from Zi to Ck prime is Euclidean distance between those 2 points minus this epsilon we have here and the norm difference between those 2 points. Why did we do this? It looks a little bit strange, but this is a cool thing because now this work is not only trial and error. Okay, let's try some cost function, let's see what happens if we can train it, and then, you know, provide some accuracy results. This is based on a mathematical derivation and foundation. Because if we look at the cost function with this new dissimilarity measure in prototypical networks between embedding points and centroids, we derive basically the gradients that, after all, is the backbone backpropagation. It is revealed by doing the math, basically, that by defining these class conditional dissimilarity measures, we will have, when Z, so basically in the end, Z will be attracted to the correct prototype, and at the same time, it will be forced to have the same norm as that prototype. On the other way, it will be repelled from non-correct prototype, but still be forced to have the same norm as that prototype, which is not from the same class as that particular point. However, this means that basically points are attracted and repelled to correct and incorrect prototypes as it should be, but they are forced to be on the sphere of, in this space of the representation of the neural network. So this is what we then basically implement. We learn the normalization by the network. We do experiments in the traditional few-shot learning way. We get really good results by regularizing the network and learning the regularization as an integral part of the whole system, not forcing it by some back projection onto a sphere, but by learning to embed onto the spheres in a natural way by defining a new dissimilarity measure. So in bold, you can see SAN-PN Rs, and you can see that it improves upon the baseline prototypical network, the state of the art from before. And basically, we've tried different embedding networks and different types of network, and in all cases, we have an improvement. And we can also see by these we have here are basically 3 different ways to do prototypical networks. On the right-hand side, you see our method. You can see that the norm of the embedding points become the same. That's what you see on the right, and that's our method. On the left, you can see other methods that also embed by few-shot learning, but data points do not end up on the sphere. We can see that clearly from these plots, and it's also reflected in the accuracy of the methods, where ours perform better. So this is a combination of starting out from very applied work, ending up in quite basic work where we have to go into the math. And this is what I think is really, really cool. And it could also very well be that this work, basic work in few-shot learning, will be implemented in the operational system to monitor, for instance, power lines by us and by eSmart systems. All right, so I'm not sure if you can hear me, Klaus, but this concludes the talk. To summarize, industrial project, a company, a university group, starting out for a year, for 2 years, engineering, create training data, get a system up and running. It is up and running. Over the time, some challenges came up, and then we went into a more basic research direction to try to solve these challenges. And I'm very happy about this kind of applied basic type of research, and also very happy about this collaboration we've had. All right, Klaus, thank you.
Thank you very much, Robert, for a very exciting and interesting talk. And I think also a great example in this field of how this advanced engineering and often leads to basic research. So that was very interesting to hear. We have a couple of questions here, and if others also want to ask questions, please post them in the chat or in the question and answer button under the screen. So the first question here we have is, I will just read them, Robert. Thank you for the interesting presentation. What kind of faults this system can and cannot detect? For example, current overloads, heated parts, etc.
Yeah, so that's a very good question. So thanks to the one that asked this question. So basically now I didn't have the time to go into the problem setting in the detail I should have maybe. So we have some 40-50 different types of classes basically in our original problem. And for instance, when it comes to the insulators, only there we have like 20 different ones. So you know these insulators where the power lines are attached. So we, at the same time, we want to classify insulators into the correct type, but also into the class that the insulator is broken. So basically both, for instance, insulator of a certain type, but also this certain type of insulator is not okay. There's something wrong with it. So it means we have lots and lots of classes. But this we can do pretty well with the insulators and also even woodpecker holes, because we have wooden masts. When it comes to heating, that's actually a very good comment, because something we've been talking or thinking about in the past is, for instance, thermal imaging. But this is only optical imaging, so we don't really have any way, as far as I know at least, to pick up on heating. So that is not part of the equation right now. But basically, problems with the wood or with insulators, and also on top of the masts, there's supposed to be a metal cap on top of the mast, and this is often missing. So that's also one category that is a part of this training the neural network. Is the metal cap there or not?
I will continue with, it is 3 questions from Abel Deradman Ali Ahmed. So this second question is, the model is trained on synthetic data. I am wondering about the performance on real data.
Yeah, okay. So the LSNet, which is the one that tries to detect the power lines themselves, that one is only trained on synthetic data. But in reality, you know, when it is operational, it's only on real data. So when I showed you the performance of the method, it was on actual real power lines in Norway with optical cameras. But when it came to the first part, I didn't really go into much detail, but where you could see the video of the drone approaching the power mast, that one is actually trained on real data. I mean, manually annotated real data. So that's not the synthetic data part. That very first video was on real data, manually annotated by lots of volunteers that eSmart systems have had working on manual annotation. It's taken quite a long time to do that.
Thank you, Robert. Question number 3 is where this model should be deployed in the drone device or in the central station. So should it be deployed in the drone itself or in the central station? So what are the limitations for the deployment?
Oh yeah, that's a very good question. So right now, it's a central processing. You know, it's not on the drone itself. I should probably have asked maybe my collaborators at eSmart a little bit more about this particular thing, because it's very, very important. You know, what kind of load can the drone carry, battery capacity, and so on. And also, you know, what is possible to do on the drone itself. I think this is more in the future, because right now it's done on a central location, and basically images are, you know, transmitted to somewhere else, and the processing is not done on the drone itself.
So thank you. We also have questions from Morten Goodwin. Great talk. He says, YOLO argues that they do overlapping, but each object is connected to only one grid. Objects can be bigger than the grid cells. Is this different with LSNet? Could you explain again how LSNet detects overlapping objects and YOLO does not? Can LSNet have 2 objects in one grid? If so, how?
All right, I know, Morten, this was a very good question. So for us, the starting point was that our objects extends over more grids. So in a YOLO way of thinking, then if you have a car or something, and it's bigger than the grid cells, then you might have problems. But you can have more than one object in each grid cell in YOLO. I don't remember right now exactly the number, but I think within each grid cell, a certain number of objects are proposed in YOLO, if I remember correctly. For us, there's just one object, and that's line segment. And right now it's only one, and it's the longest one, the biggest line segment that we are trying to basically find the start and end point of. And if the line extends over a long range, many, many pixels in the image, and we use non-overlapping grids, then at the border between grids, we could miss some pixels. So it could appear to be non-connected lines that we detect. But by having the overlap, we kind of fill the gap. So I'm not at all sure if this answers Morten's question, but for us at least, we started out with non-overlapping grids. We had these problems with detected lines not being connected. And then we realized that we could implement overlapping grids, and to have more grids than just the kind of the 4 or whatever non-overlapping grids. And we could do this by neural networks. That's kind of a little bit important, that the grids are also implemented by convolutional neural networks, these 2x2 convolutions I talked about. So anyway, Morten, you can ask me afterwards if you have more detailed questions.
Yep, we will stay here. We will close the meeting at 3, but we can stay. Those of you who wants to stay here, I will try to open up for a conversation. Morten has a second question. It's about a very new version of YOLO, version 4, that came out last week. Any idea of how this changes with YOLO version 4? So that's let's see how updated you are, Robert.
I have to admit, I'm not aware of the latest from last week. No, I'm really not aware of that one. At least when we submitted our paper, then we sort of had a difference in the way that these grids were performed. But at the same time, I mean, it's not a revolutionary idea to go from non-overlapping grids to overlapping grids like we did. So I'm not surprised if this is now the case also for YOLO, and maybe in the same way as we have done, for all I know. But I just don't know that last paper from last week.
Yes, you get some thumbs up from Morten here. A very last question. I'm a bit interested in a rumor about the training data for component classification. Is it true the data is too good for in practice usage because of the extreme resolution used? That is from Christer Mathisen.
That I'm not really sort of sure about this this rumor, but power companies in Norway, for instance, here in Tromsø, have provided images, and basically helicopter images, for instance, to be used, and it could be that there's a mismatch in the resolution of training images towards what is maybe the sort of most common when it comes to the drones. But this I would have to ask basically collaborators at eSmart how this is.
So thank you very much, Robert. This was a great talk.
If I could just add, Claes, on, for instance, on the LSNet, when giving some talks about the LSNet, other places, also internationally, some people have seen potential use, for instance, railways or in medical imaging to try to detect linear structures. So even though this work was carried out in the context of power lines, could maybe be some potential outside of this application where you have similar problems that you need to handle. But of course, you need this kind of pixel-based training data. We need to know for every pixel whether we have a line, whether this pixel belongs to line segment or not. And this is of course not always possible to have in your training data.
Thank you. And as Robert said, the Northern Lights Deep Learning Workshop, it's absolutely to recommend. It is a great workshop and conference. So please attend that next year. We will have these Friday afternoon seminars every Friday now. And next week is Ole Kristoffer Granmo. He's the director of CARE and from the University of Agder. He will talk about the recent advances in the settling machines. And I just posted out a link on the chat. I hope all of you can see that. So it's just to go in and register now. And that concludes today's seminar. I will try to open up for participation to speak for all of you if some of you want to stay here and ask some questions to Robert. Okay? If not, thank you to all of you. Bye.
Thank you, everybody. Thank you.
Let's see, Robert, if